Welcome to the comprehensive guide on tensor calculus. Tensors are often shrouded in mystery and perceived as a daunting task to learn. Are tensors really difficult to learn? How will you start learning tensor calculus? What are the best books and resources you should start with? Do they at all have any practical applications, or it is just a theoretical approach? Well, I'm going to answer all these questions and give you a comprehensive, detailed and a step-by-step guide on learning tensor calculus. You will not only learn the fundamentals but also clear some misconceptions, learn the important features of tensor and how they play an important pivotal role in framing Einstein's field equations and many more. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to a comprehensive overview on learning tensor calculus, which starts with the basics and most importantly give you a complete understanding of the books and the approach and everything. Well, first we start understanding what is a tensor. And as we see, most of the physics and mathematical terms have their root and etymology in either Greek and Latin language. Tensor is also not an exception. You see, the word tensor comes from the Latin tender, which means stretch. So in anatomy, we call it a muscle that tightens or stretches a part of the body. That means we can understand that it has something to do with stretching, pulling, etc. Now, this is something which is related to anatomy or the physiology, but what it has to do with physics and mathematics. Does it have any relevance related to stretching and pulling? Yes, it does. And this is what we are going to explore now in this example. Now, consider a sphere which has got some amount of information over here, which I have marked in red. Now, if I extend or stretch the sphere, it would become what is called an oblate spheroid. So once the sphere takes a deformed shape, that means the information from here will also be stretched. And that is why we tell that how will you come to know about that specific stretched information. So that is what we say, that tensors are something which stores some amount of stretching information. As it started with the root tender, which means stretching, etc. So tensor basically is I would say storing some information which is related to stretching. Now this is something which is called a very easy or a layman's approach, but in mathematical term what we call is this: a set of components or functions of the coordinates of any space that transforms linearly between coordinate system. Don't worry if you don't understand the red underlined word linearly between coordinate system. I'm going to explain and make it pretty simple. So first we understand that tensor is something which is related to stretching, and the stretching information is stored in the mathematical concept which is called tensor. So technically we can say that a tensor is a mathematical object that generalizes scalars, vectors and matrices to higher dimension. Now what is actually tensor? Let us consider this kind of a network. We can call it either a data or a network of data. So we say that a tensor is a kind of a flexible data structure. It can store numbers in a grid of multiple dimensions. Now hold on, when I say it can store data in multiple grids in multiple dimensions, I mean something really serious and something deep, which I'm going to explore in the next part of the video. And it organizes and manipulates data in a very, very complex way. So it actually is a flexible data structure. It stores in multiple grid of multiple dimensions, and it organizes in a very complex way. So the mathematical definition tells that a tensor is a mathematical object that describes a multilinear relationship. Why multilinear? Because it stores in multiple dimensions between set of algebraic objects related to a vector space. So tensors actually can map between different set of objects like scalars, etc. and so on. So we understand that because it stores stretched information, it stores in a of multiple dimensions in a complex way, and it is very flexible in it is a flexible data structure. Now, having said and understood basically what is tensor, let us look into some of the important aspects, or we can call characteristics of tensor. First is that tensors are vectors, something like vectors which have not a single direction, but rather it points into multiple directions. As an example, I have taken this cube, which is a 3-dimension x, y and z, but it has also got another dimension and maybe more. The second feature tells that tensors have properties of both vectors and scalars, which we will explore, like area, stress, etc. The next characteristic tells that a tensor is not a scalar, a vector or anything, but actually it is just an abstract quantity. Now, you might counter me that you just have told that tensors are vectors. Then again you are telling that tensor is not a scalar or vector. What is the meaning? I deliberately made this example, so from the first example you grasp the concept that tensors are vectors, but they do not point in a single direction, and I am moving slowly to the more abstract and the actual definition. So from there we understand that tensors are actually abstract geometrical objects that describe the linear relationship between geometrical, numerical and other tensile vectors. Remember that this term tensile is an incorrect English, but I have just made it to give you a feel that tensor or tensoral or tensile, something which relates to that. So this is an abstract mathematical concept that obeys coordinate transformation and has geometrical objects that transforms linearly, and it is neither a scalar or a vector. It is a kind of an abstract concept. So this abstract concept will become more, I would say, concrete as we move into the next part of the video. Now, having understood a basic intuitive understanding of a tensor, it is now the time that we should understand that why are we cracking our brain and watching the video, taking notes. The question is that why should we learn tensor? Does it really have any meaning in our study of mathematics, physics, etc.? Coming up in the next part of the video, why you should learn tensor. Now, if I consider you are taking tensor in terms of a geometric approach, then first comes differential geometry. So you understand that these are properties which describes the curvature of space, and this curvature in return explains a lot about the physics and mathematics of curved surfaces, manifolds, etc. So if you're learning differential geometry, automatically you have to learn tensors. Now in linear algebra, I mean to say this is a must. You can say it is a mandatory. Tensors are used to represent linear transformations. So if you are learning linear algebra, I mean to say a little bit in the intermediate level, you will see that tensors are coming. So you should study tensors in order to learn, I would say, linear algebra much better. Obviously, one of the most important concept is the Einstein field equation, and we will see how tensors play a very major role in terms of general relativity. Now in quantum mechanics also tensors are used because tensors do represent what are called vectors, operators and observables. Furthermore, in modern science, we say that tensors are very important in terms of computer vision, because all those, in social media, Instagram and Facebook, all those huge amount of, I would say, images or the data that you see are actually now stored in multi-dimensional arrays, and they can represent actually various types of data, and we will soon see that what is this multi-dimensional array and how computers actually store. So you see computers are also taking care of tensors, or in the other way tensors do take care of computer vision. Electromagnetism, I think this is quite evident because Maxwell's equations are often used as tensor notation, electric fields, magnetic fields and so on. Yes, fluid mechanics, tensors are used in fluid mechanics because it expresses stress, strain and other areas. And finally, crystallography and material science, because remember, tensors actually started not with physics, not with mathematics, but to study the characteristics of crystals. Crystals, because they represent, when they are heated up, they expand in different directions, which vectors actually cannot take care. So definitely crystallography, material science, piezoelectric, elasticity, everything are taken care by tensors. So you see it starting from computer vision to basic abstract mathematics to differential geometry and coming into real life applications like crystallography, tensors are everywhere. So you really cannot avoid tensors. Now you might have a questions, we understood all this, but what are the real life applications of tensors? Let us look into the real life applications of tensors, which will be explained in this part of the video. The first thing which comes obviously is as a whole data representation. Now you see that today we have got mobiles, every time we are taking photographs, social media is flooded with photographs and a huge amount of data. So the representation of the data cannot be done in a usual manner or in the general computer sense. Computer programming. So data is naturally recognized in higher dimensions, videos, etc. all are using tensors. Most importantly, deep learning and neural network, we will see those softwares and how learning tensors are actually advantageous. So neural networks, layers, activations, they require tensors. So a simple feed-forward neural network can be viewed as a series of tensor transformations which actually takes place. Numerical computation, as you see the GPUs and TPUs and the modern hardware, as we are running through a lot of complicated softwares, etc. So numerical computation is also being organized, I would say, and optimized for tensor operations. So deep learning, neural network, numerical computation, they actually are, I would say, worked on the tensors. So you understand the importance. Now in mathematics we see that machine learning, which actually computes what is called higher order derivatives, tensors allow for the computation of higher order derivatives. You might say that is it that without tensor higher order derivatives were not being calculated earlier? Definitely, but with the advent of the huge amount of data and AI coming up, higher order derivatives and physical simulations, etc. would be requiring tensors. This is something kind of a repetition, so I won't elaborate further. Image processing, all the data and the image are being stored in the form of tensors. So image convolution of operations where you apply a filter tensor to extract images. Data analysis, yes, a huge amount of data in every part. I mean to say not only in social media, every part the data analysis is being done with the help of tensors, and most importantly climate modeling. Because again, when you model a climate of a specific zone, you have a multi-dimensional climate data. And the general way of storing the data, which we used to do, is not being done through general, computation. So it helps scientists understand and predict complex climate patterns and trends. So having said this, we can summarize that tensors are important. The reason is simple, that it provides a unified and efficient way, and the multi-dimensional data in either way, in image processing, in computer, in neural network, in any simulation, it enables advancements in a wide range of fields, from AI to deep learning to physics, engineering, scientific research. So I would say they underpin many of the computational tools and models, and they try to innovate on those domains. So this is why you can now see that starting from computer processing, data management, deep learning, higher order derivatives, climate modeling, everything are using tensors. The basic thing is simple, because they help us in a very unified, efficient and simple manner to store data which are coming from multi-purpose, I would say, avenues, etc. Now this is what we call the usage of tensors, which are other than physics or mathematics, or practical usage. Now I would like to talk on a very I won't say upcoming, it is a cutting edge technology of Google, and how tensors are actually helping this one, which is called Tensorflow and Tensors. I hope this would be a very interesting part of the video. Coming up next, what is machine learning, data science, etc., and how tensors are used. Now, if I take in a very simple language, you understand TensorFlow is nothing but a powerful tool created by Google to simplify building and using machine learning models. This is a very simple approach. So these models are essentially computer programs that can learn and improve from data, just like the way we learn from experience. So that this software is called TensorFlow. Remember, it is an open source software library which is developed by Google. Now you might say that why I am talking of machine learning, etc. Does it have any relevance to the original tensor mathematics? Yes, it does. And you see, November 2015, Google released its open source framework, and it supports deep learning and neural networks. Now, I would give you a simple example. So first is that building training machines and learning models. So TensorFlow provides tools and functionalities for constructing various machine learning models, especially, remember, deep neural networks. So with this, you can define the layers, specify the type of operations which each layer performs on the data, I mean to say tensors, and configure the training process. Once you have trained a model in TensorFlow, you can deploy it for various purposes. TensorFlow allows you to run your model on different platforms, including desktops, mobile devices, servers, and even embedded systems. TensorFlow benefits from a vast and active community of developers and researchers. This translates to extensive documentation tutorials and pre-built models that you can leverage of your projects. So what we can say is this: TensorFlow actually acts as a powerful toolbox for machine learning tasks. It provides the building block, which are the tensors, and creates functionalities which can deploy learning models that can learn from data. So remember that the underpinning of this entire idea is nothing but the original mathematical tensors which we are learning right now. Further, TensorFlow also uses what is called multidimensional arrays, because at its core, TensorFlow mirrors the mathematical concepts of tensors. I mean to say mathematical tensors. Just as a tensor in mathematics represents multidimensional arrays, tensor in a TensorFlow is similar data structure. It holds numerical data arranged in a grid with multiple dimensions. This is the text which I was talking about. Now, data types. Remember that like mathematical tensors, TensorFlow tensors can hold various data types, which are, say for example, integers, floats, complex numbers, strings, etc. So the appropriate data type is chosen based on the specific machine learning tasks. Operations. Yes, TensorFlow supports a wide range of operations of tensors which are similar to mathematical operations, which includes element-wise operations. That means addition, subtraction, modification, multiplication, division, etc. Linear algebra operations like matrix multiplication, vector addition, dot product, etc. And tensor informations where reshaping, slicing, broadcasting operations that manipulate to structure and dimensions of tensors. So these are actually, I mean to say, the TensorFlow of Google at the base root level is the mathematics of tensor. Nothing, I mean to say, nothing more than that. Now here comes another important part which TensorFlow obviously supports, and we will look more examples in this today's video, is that if it is not a direct equivalent, TensorFlow actually can undergo transformation during operations like convolutions in convolution neural network. I am not expanding what is convolution. It is a technical term which you can look into Google. These transformations loosely relate to how tensors in physics might transfer under coordinate changes, although the specific content is a little bit different. Now, it gives also importance of shape, because similar to mathematical tensors, the shape of a TensorFlow tensor, that means the number of elements which is there in each dimension, is crucial. So it determines the type of operation that can be performed on how the tensor interacts with other tensor within a machine learning models. So finally, we can summarize that TensorFlow actually leverages or elevates the power and versatility of mathematical tensors, which creates some more foundation for building the manipulating data in the context of machine learning. So if you understand the basic mathematical tensors which we are learning here, it would provide a strong foundation for working effectively with TensorFlow. So I think that if you're going along with TensorFlow, which is a very strong product of Google, learning the mathematical or the usual conventional tensors is immensely going to help you, because you just saw that how these are all related. Now, is it that only TensorFlow is the product, or I would say developed by Google, that includes the mathematics of tensors? No. let us look into some of the new softwares, I would say developments, which actually supports the mathematics of tensor. Now TensorFlow we have already looked, as the name suggests, TensorFlow relies on tensors as its core data structure. The next one is called PyTorch. Right, and this is another popular deep learning frame network. It's developed by Facebook, and tensors in PyTorch are similar to NumPy, if you have heard about this word NumPy arrays, with added functionalities for automatic differentiation. So the underlying concept, remember, align with the mathematical tensors, which enables the efficient manipulation and computation of multidimensional data. Yes, here it is. It is called Keras. Now this is a high-level API which can be used on top of TensorFlow or other frameworks like PyTorch. So Keras provide a more user-friendly interface, right? And it was developed by Francois Chollet, and it was a part of what is called ONEROS project. So this actually, I would say, helps again understanding tensors for working with Keras effectively. Now this is developed by UC Berkeley Institute. It is called CAFE. So although it is less effectively maintained now, CAFE was an earlier deep learning framework that also exploits or utilizes tensor for data representation. And finally, MXNet, which was developed by Amazon, is another open source deep learning framework. So MXNet incorporates tensors as its foundational data structure. So you can say, similar to other frameworks, tensors in MXNet enable sufficient handling of multidimensional data commonly used in machine learning tasks. So all in all this PyTorch and Keras and CAFE and use those NumPy. I have not mentioned NumPy, otherwise I would have mentioned NumPy, is definitely a very powerful tool. So what it says is that in essence, deep learning frameworks borrow the power and elegance of mathematical tensors, obviously, and it to create an efficient scalable tools. So remember, the last line is very important. Understanding mathematical tensor is very important because it provides a strong foundation for effectively working with these frameworks. So now that you have understood that what are the frameworks, TensorFlow, and other than TensorFlow, what are the other companies which heavily relies on the mathematics of tensors. So if you're looking into machine learning data science, you also need to learn tensors. Now we talked about one concept which you remembered, that coordinate transformation, and it has something to do with a very central idea, tensors and coordinate transformation. Now what do I mean by that? I am now going to explain. Remember, this is the most elegant, efficient and the most powerful central power of tensor calculus. And what is that? I'm going to explain it in the next part of the video. So as you have already understood that this is something related to transformation rule. Now if I get a xy, I mean to say just a Cartesian coordinate, and if I get this kind of a crazy coordinates, then if I'm moving from a flat space to a curved space, the data, as you see, the red one, also get curved, also get stretched or squished or whatever, depending on the deformation of the manifold. I should use the word geometry because I have not defined manifold right now. So when we are moving from flat space to curved space, this is a deformation which is happening, and the transformation rules maintains the deformation, yet the measurement of the main thing remains the same. So as I have mentioned that the object from here gets stretched over here. But remember one thing, that if the object gets stretched, the laws of the physics should be the same. So here is a coordinate system, and I've got a data something like that, a red arrow or something. Now if I rotate this, remember the laws of nature should be the same. So this data, the red one, you see, get a little bit, I would say, slanted on the rotated axis, which is on the top. But what does it say? That if the coordinate system is rotated, then how do we measure things? How to keep the measurement invariant in spite of those change of coordinates from flat to curve, from spherical to oblate spheroid, and from a fixed coordinate system to a rotated coordinate system. So the basic idea is that the laws of nature should be invariant under any kind of a transformation. Now you might question me that what happens with the transformation? The idea is that tensor is the key which maintains the laws of nature to be invariant, whatever might happen to the coordinate system. Now let me explain it with a very simple example. Suppose this person is throwing a volleyball, and this is the way he is throwing, and on the another frame of reference, if it is a rotated axis, also it would be the same. That means that for that person will be throwing a ball. This is an event. I mean to say, I'm just talking in terms of not special relativity, but in general terms, that the same event will be registered in the rotated axis. So the events will be measured in the same way in all frames of reference, isn't it? Now here is something, another event. Now instead of rotation, what happens if I stretch the axis like this? So the axis is extended, but again the event will measure the same thing. So events will be measured in the same way, irrespective of the change in the coordinates. So just the same way this part gets extended in an oblate spheroid, the famous saying of Einstein says that the general laws of nature must be expressed by identical equations relative to all other systems, whichever way they are moving. And who does it? The tensors actually does it. I would say the tensors actually perform this kind of an idea. So the basic idea remains the same, that in case of anything which is happening in terms of rotation or in terms of the geometry, let us term it as a geometry or a manifold, but the measurement would be the same, and there should not be any kind of a change in terms of the measurement, and that is basically the idea of the tensors. So if we see a kind of a transformation rule of tensor in terms of the change of the coordinate system, then what we see also, if I take V for example, and that is basically what is called a vector, then it denotes what? The vector actually solves a wide range of problem in physics and engineering, we know that, and they provide a strong foundation to understand tensors. So we say that vectors as objects with magnitude and direction. So vectors can have more than one kind of component, and those are different types of components obviously. And what happens is that vectors as objects with components that transform between coordinate system in a very specific and predictable way. So when we say a specific and predictable way, what do we mean? We mean that we have to specify the rules. Okay. Now all these things, I know it is a little bit abstract. Let me explain you with a kind of a very visual example. The question is that what happens to a vector? We have seen just now that vectors actually solves a wide range of problems. They provide a foundation, and the question is that what will happen if we specify the rules? So what happens to a vector when you can change the coordinate system in which you are representing the vector? Nothing happens. That means, say for example, the vector components may be different in the new coordinate system. So if I take this kind of a room, say for example, and if we are measuring, say for example, the temperature of the room, which is in Fahrenheit or centigrade. Now the thing is that whether you measure the room's temperature in Celsius or Fahrenheit, it does not make the room feel hotter or better, right? So it would be the same, and that is basically the idea. Now I would like to take an example. You see there is a sofa on the right hand side and there is a lampshade. Now why I am taking this example, it will just become clear in the next part of the video. So from here what you can understand is that the vector's components may be different in the new coordinate system. I mean to say from Fahrenheit, for example, you change to centigrade. These are the change in terms of vector components, and from centigrade you move to another scale, but the temperature won't change, or you won't feel cooler, etc. So the vector itself won't change. Now I will just explain it another example. Now this is a room and I am looking at this room, say for example here, the first case. Now I tilt my head on the a little bit upper side. I tilt my head right on the top and I try to look around the same room. Now what happens is that the size of the room won't change. If I look in this direction, if I move my head from here to here, it won't change. Similarly, if I look at the same room and I am looking right from here, I have made a point, say for example this black dot, and this black dot actually represents a kind of a coordinate system. Again in the same way I have tilted my head. I mean to say I am looking upstairs, a little bit up. What will happen? This dot will actually move, or I would say the coordinate would move in this direction, and I can plot that on a XYZ Cartesian coordinate. So what I'm trying to tell is this: the room itself does not, under such a change of coordinate, does not change under the system. Mathematically, we call this as something which is invariant. Now, if I stretch the sofa, say for example, if I stretch the sofa like this, then possibly what happens is that we can measure it in any other coordinate system as m or something else. So the room itself does not change under such a coordinates, and this is what we call mathematically invariant. But the coordinates, you see the black dot has moved from this point to this point. I won't say moved, but we can measure that measurement, that if I'm looking in this way, the point should be this, and if I'm looking up way, then obviously the arrow should be pointing a little bit upwards. So when coordinate system transformation, whatever rotation, squishing, etc. is taking place, what precisely transpires with a vector during a coordinate system? So here is a Cartesian coordinate system, and you can see the location of the origin has not changed. So x has been rotated to x prime, y has been rotated to y prime. This one, x and y. So it is tilted in counterclockwise direction, and this angle, as you can see, the theta, is moved from this part to this part. So the rotated axes are labeled as x prime and y prime and are drawn using dashed lines in order to distinguish them from the original axis. However, the main vector, whatever if you are measuring, would remain the same. To make things easier, I would like to show you a flat coordinate system, and this is the vector A. I am measuring the components of the vector as AY, and I am measuring the x coordinate system as AX. Now what I do is that I will measure this as blue dotted lines. Now see the animation on the left hand side. What I do, I move from a flat space to a curved space. So the flat space is still x and y, and the curved space is this one, x prime and y prime. Now I will maintain the same vector, and what I is going to do, if I am changing the components of the vector which are marked by blue dotted lines, you see that now this a prime x is much bigger than the original x, and the a prime y is also bigger than the original ay, and the vectors of the components have changed, but however the main vector ax, the a, which has become now our a prime, has not changed. Nothing has changed, right? Now in the same way, a prime x is longer, a prime y is longer, but a is invariant from flat space to curved space. Now why I am telling you this? Because this is what is the power of tensors. This is what the central idea of tensor, that the coordinate system transformation, how does it register? In the same way, when I rotate this coordinate system, you see it is rotated from the left hand side and the right hand side. So you see this ax now becomes this one, and ay becomes this one. You see the a prime x, how it is, and you see the a prime y is now shorter than the left hand side a prime ay. So the static frame of reference and the rotated frame of reference, this one is shorter and this one is much bigger. But note one thing, that the main vector a has remained the same. So tensor is basically this tool to register the measurement of a vector, and as we move up into complicated physics, covariant differentiation, etc., whatever, the basic idea is that the laws of the physics are remaining the same, whatever is happening to the geometry of space-time. Okay, now you might think that we are talking about this in terms of mathematics. I mean to say, I'm showing you the Cartesian coordinate and the spherical or maybe the curved space-time, etc. But what is the usage of tensors in physics? Because we are most interested into physics, right? So what are the usage of tensors and how it is useful in physics, coming up into the next part of the video. So as you can see, that first thing is that tensors describe what are called physical properties. Physical properties in the sense that strength tensor captures the internal forces within a material. Strain tensor, the tensor describes the deformation of material. Momentum tensor encodes the momentum of carried by particles. Electromagnetic tensor, this shows that Maxwell tensor unifies electric and magnetic fields, and so on. So it actually registers the physical properties. Now, transformation under coordinate system, I think I have just shown you a lot of example, rotation, flipping, etc. So the basic advantage of tensor is they transform in a specific way under change in coordinate system. Obviously, transformation will happen, but it follows certain rules. So this ensures that physical laws remain the same regardless of the reference frame to describe them. And obviously our favorite topic, general theory of relativity, because we will see in this video that how each and every component of Einstein's field equations are being built and described by what is called tensors. Other than this, you see fluid dynamics, tensors are used in the study of fluid dynamics, because to describe the flow of fluids including liquids and gases, tensor is used to represent quantities such as velocity, pressure, stress and strain and so on. Solid mechanics, yes, tensor is used in the study of solid mechanics to describe the mechanical behavior. Now my question to you is that do quantum mechanics also use tensors? Now this is something which I am not going to talk, but rather I will wait for your comment. If you really know, and whatever you know, if you want to contribute, please do let me know that how quantum mechanics also use such tensors, and let me know in the comment box. Now we have been talking of general relativity, how tensors frame the mathematical equations of Einstein. Now it is the time, and in this part of the video we are going to look into just overall how tensors frame and make a foundation of Einstein's general relativity, coming up in the next part of the video. So what you see is a very familiar equation which is called Einstein field equations. Now first of all, these components R mu nu measures the dimension of space-time. That means how do we measure the space-time? So 0 is the time, 1 is the x-axis, 2 is the y-axis and z is the three-dimensional, the number 3 axis. Same happens with G mu nu, which measures 4 dimension of space-time. G mu nu also represents 4 dimension of space-time, and T mu nu also denotes the space-time. And mu nu actually denotes what are called the indices. Just like alpha beta, you can even put alpha beta, no problem. This is the convention which shows the indices. So overall what we can see is that 4 plus 4 plus 4 plus 4, it takes up a total of 16 equations. Now you might say, do we really study 16 partial differential equations in Einstein field equation? The answer is no, and I'm going to show you why it is no. But before that, a quick idea that what are those tensors that we are talking about. Now in this equation, as you see that there are certain components which you already know. I mean to say some things which you already know. For example, lambda, you know it was called the cosmological constant. C4 obviously is the speed of light. 8 pi is a constant, and G is the good old gravitational constant of Isaac Newton. So these are all constants. So we know what are those constants, and I mean to say we know the values, etc. We are really not worried about. But what we are worried about are the unknown ideas. I mean to say those which vary. So this first R is what is called the Ricci curvature tensor. Now hold on, if you're really willing to know this, I have a separate set of video. I'm going to tell you how to watch that. So it talks about how a volume of matter changes when it moves from flat space to a curved space. Remember, when we are talking about volume, I mean to say obviously differential volume. The next, this R, the second R, is what is called Ricci scalar. And what it denotes is that it keeps track how the size of a ball deviates from Euclidean space. Then we come to the very important and central part of Einstein's field equation, which is called metric tensor, and it talks about the causal structure of space-time. That means how the distances are actually measured. And finally we come to this Riemann curvature tensor, which is a hidden tensor. I have explained earlier in the videos that it is a contraction of the Ricci and the curvature scalar, which I'm not going to explain in here. And here comes the last T, which is called the stress energy momentum tensor. This keeps track of the movement or the matter movement through space-time. Now, as I told you that we are actually not studying those 16 components of Einstein's field equation. What are those which we are studying? Let's see. Now, this is what is called the metric tensor. I mean to say, I'm not saying this what the G00 and derivation. You can look into my playlist in General Relativity and Physics for Students. You will find what are those. But what is important is that out of those 4 plus 4 plus 4 plus 4, 16 components, 6 component gets cancelled out. And I'm going to show what are those components. So we get finally 10 components. So this G10 and 01 gets cancelled out. 02 and 20 gets cancelled out. 03 and 30 gets cancelled out, and so on. And once they get cancelled out, what remains are only the 10 components, which is this one. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So we are not studying 16, we are studying 10 components. And because this is a symmetric tensor, that means you can swap around the indices. G mu nu can become G nu mu. And swapping means whether you measure in the clockwise or anti-clockwise, the measurement will always be the same. So metric tensor actually is a very fundamental object of study, and it actually captures what is called the distance, volume, curvature. And I can show you if these are the points. Just for an analogy, you can think of them as what you call distances between a Cartesian system, and these are the distances. So actually the metric tensor measures those distances, etc. But remember, this is just an analogy. It is not as simple as this. And if you are willing to learn a little bit more about what is called Einstein's field equation, this is the video. Go to my playlist in General Relativity, and lesson number 21 is a very beginner's approach to Einstein's field equations. So the basic idea of showing you this is nothing that all the equations and all the major ideas of relativity, general relativity, are coming from tensors. So because we are moving from a flat space to a curved space, because we are moving from a usual Euclidean geometry to a spherical, hyperbolic, or we can say non-Euclidean geometry, because we are registering what is called coordinate transformation, yet the events shall be measured in the same thing, and because the curvature of space-time is being measured in terms of Einstein's field equations, tensors become a very central part of our understanding in general relativity. So this is again another important point which shows that you really cannot escape from tensors, because if you're interested in understanding Einstein's general relativity, you have to study tensors. Now, you might be thinking that you are suffering from learning tensors, it is so difficult, etc. But remember, you are absolutely not an exception. One of the greatest and the most brilliant mind of our times, Albert Einstein, also suffered from understanding tensors. And there is a beautiful history and a beautiful story which I'm going to tell, because you are not only finding tensors to be difficult, even Einstein found it. How Einstein found it, and what are the way Einstein finally solved it, coming up in the next part of the video. Now, Einstein actually left Prague around July 1912, and in August 1912, Einstein and his family arrived back in Zurich, and on the 10th of that month, they were officially registered at this house which you're looking on the left hand side of the screen, and this apartment called Hofstrasse 116. It's famous, I mean to say, it has now become a tourist spot. Now, sometime between August 10 and August 16, it became clear to him that Einstein, that Riemannian geometry is the correct mathematical tool for what we now call general relativity theory. Now, the impact of this abrupt realization for Einstein was to change the outlook on physics and physical theory for the rest of the life. And the next 3 years of his life become the most strenuous period. Now, you see that his friend actually, Marcel Grossman, helped him to accommodate and get into the family. And Grossman was actually busy preparing a lecture on the 5th International Conference. And remember, Marcel Grossman is known to be a master of differential geometry. And after arriving at Zurich, Einstein and Grossman started a collaboration. And he was finding it difficult to frame what is called a covariant theory of gravity. And this is actually the German word and I won't pronounce it, it would be incorrect. What it means is that, Grossman, you must help me, otherwise I would go crazy. That means Einstein was totally unaware about the Riemannian geometry, Ricci curvature tensor, etc. And it was with the help of Grossman, that he was seeking the help of Grossman, that please help me, otherwise I won't be able to find out the relative theory. Now, I don't know whether you have heard about this person. Abraham Pace is a very famous historian and was a colleague for a brief time with Einstein. Now, this book I would strongly suggest you to read is called Subtle is the Lord. And in this book, he actually writes what Einstein told him. So he tells that I have a vivid, though not verbatim, memory of Einstein's reply. And he told Grossman of his problems and asked him to please go to the library and see if there existed an appropriate geometry to handle such questions. And you know what happened? The next day, Grossman returned and said that there indeed was such a geometry, which is called Riemannian geometry. And we would soon see that it was Grossman who was telling that he himself, I mean to say Marcel Grossman, was not at all very confident about this complicated mathematics. So Einstein told Grossman that he needed a geometry which allowed for the most general transformation, which would leave the equation so and so invariant. And Grossman replied that the answer only lies in Riemannian geometry. So this is the famous photograph of Marcel Grossman and Einstein. And in this book, what Abraham Pace writes is this. Grossman added that is a terrible mess which physicists should not involve, I mean to say the Riemannian mathematics. And Einstein then asked if there were any other geometries that he could use. And Grossman straight away told no, and pointed out that differential equations of Riemannian geometry are non-linear and it is a very bad news. But Einstein replied on his remark that he thought, on the contrary, that was a great advantage. So what it tells about is that Abraham Pace and that Einstein was severely struggling from understanding, and he was at all not aware about Riemannian geometry, and it was Grossman who helped him. And on the October 29th, he actually wrote a letter to Arnold Sommerfeld, and he told that I am now working on that gravitational problem, that I can overcome all difficulties with the help of a mathematician friend of mine here. And remember, who is he referring to, this mathematician friend? None other than Marcel Grossman. So I troubled over anything so much, I have gained so and so. So you can just pause and read this part of the video. So here you see some of the lines from Subtle is the Lord. This problem remains insoluble to me until 1912, when I suddenly realized that Gauss's theory of surfaces holds the key. And from him, that means from Grossman, he learned about Ricci, Riemann and so on. And this is the manuscript taken from Zurich notebook, and you can see on the left hand side the signature of Grossman. And this is actually the page actually shows how Grossman introduced Riemannian tensor in general theory of relativity. And I have just written it in the partial differential form because you won't be able to read that part. And this part actually shows Grossman's tensor of the fourth manifold. So remember, I have no intention to undermine the capacities of one of the greatest minds of Albert Einstein, but this is a historical fact, and there are a lot of research papers in archive.org also, which you can go search and read, which tells actually how Marcel Grossman helped and salvaged, I would say, Einstein's theory of relativity to give a covariant theory of gravity through what is called tensors. Now when we read and talk about tensors, we have certain amount of misconceptions, and I'm sure that you would be suffering from those misconceptions. So in this part of the video, I would be talking about what are the common misconceptions, because knowing them is definitely going to help you in your journey of understanding tensors. Now the first thing is that tensors are just not fancy matrices. Now what do I mean by that is that while tensors can be represented as multidimensional arrays, they are more general than matrices. So matrices are actually limited to 2 dimensions, while tensors can be taken up into any dimension. So remember, string theory, which talks of 11 dimensions, also uses tensors. So tensors have numerous practical applications which I have already mentioned, NumPy, TensorFlow and all those things. Now all multidimensional arrays are tensors. This is again a very big misnomer. Remember that all multidimensional arrays are not tensors, and there is a specific rule and there is a specific criteria that a tensor has to meet in order to tell that yes, this is again a tensor. So tensors must satisfy certain transformations rules under coordinate transformation, and then only these multidimensional arrays will become what is called tensors. So it is, first of all, they are not just fancy matrices, and they are not any multidimensional arrays cannot be called tensors. Also, there is a notion that you need to be a mathematical genius to learn tensors, which I won't agree. If you have the right approach, and that is the target of today's video, to give you the right approach to learn tensors systematically, and the core concept is something very similar, and I would keep you as a suspense because we are going to explore that. Also, there is a misconception that tensors is something related to theoretical. That means it is related only to pure mathematics, and I think that by this time you know, starting from fluid dynamics, general relativity, data science, artificial intelligence, deep learning network, neural network, all those have the usage of tensors. So let us move out from these myths, these misconceptions that you have to be a mathematical genius and they are multidimensional arrays and they are purely restricted to theory. No, no, no. It is something very practical, and with the basic understanding of those mathematics, you can learn tensor calculus. Now we will come to the book part, which I know you are eagerly waiting, but before that I would like to tell that there is something, again a misconception, between what is called a tensor and a tensor calculus. Let me explain to you. Now a tensor is what? It is just a mathematical object, which is, we can call it a multilinear map or a relationship, and it generalizes quantity and it carries certain set of rules where the laws of nature are invariant. However, the changes can be registered by tensor. Now when we talk about tensor calculus, that means it is a branch of knowledge, it is a branch of mathematics, and it involves what is called manipulation and analysis of tensors. So tensor calculus actually provides a powerful toolkit. You can say it is a kind of a powerful toolbox which actually understands and analyzes tensors. And tensor calculus extends the concepts of differentiation and integration into further areas. Also, it deals with addition, subtraction, multiplication, differentiation. So tensor transforms under changes in coordinate system, and this is crucial because, as I told you, the laws of the physics should be the same. So tensor and tensor calculus, tensor is the concept. This is the basic idea through which we are taking up, and tensor calculus is basically involving the manipulation of an analysis of tensors. So I'm making a pause of this video. If you want to take a note, you can have a note of what is tensor and tensor calculus. Having understood this, now we need to understand that what is the level of mathematics or the mathematical prerequisites that are required. Now I am going to divide this mathematical prerequisites into two parts. The first, which is called an absolute mandatory, that means you need to have an understanding why you would learn that level of mathematics and what is the level that you need to do. Obviously, the first thing which you just cannot avoid is linear algebra, and the reason is that linear algebra, just in a few steps you will learn in any book or so, that higher dimension arrays, matrices, etc. are it is the basic. I mean to say, it is mandatory that you must learn linear algebra to understand tensors. Yes, the level can be introductory, but I would say let us go from intermediate to advanced. Partial differential equations, I mean to say not ODEs but PDEs, multivariable calculus is a must, because all the tensor calculus when you would be using will be using multivariable calculus. So yes, it has to be again intermediate to advanced. So one is linear algebra, second is multivariable calculus, and then we move on to the third, which is called vector calculus. You cannot just avoid. Again, it is mandatory, because all those gradients and curls, etc., will be extended to tensor fields and in tensor calculus. So it has to be intermediate to advanced. Now this part, although it is optional, I mean to say the non-Euclidean geometry, because remember tensors actually deals with the non-Euclidean geometry, the curvatures, etc. So I'm not saying that you learn everything about non-Euclidean geometry, but I would suggest or request that at least have a intuitive understanding of non-Euclidean geometry, because tensors, as you know, I have written that it actually describes curvature, not flat spaces. So how it developed, how it evolved, who are the major players, and what are the things in non-Euclidean geometry, a basic introductory part would be something very essential. The second thing would be coming is called differential geometry. I would suggest, show you books. You will see the beauty is that if you're going through the book, automatically you will learn both tensor calculus and differential geometry. Yes, it is required because the curve spaces, manifolds, etc. with an advanced level would be optional, and abstract algebra, well, this is optional. I meant to say you can just skip through that because it won't be required, but if you do have, you can. Now, because linear algebra is the first and the basic mandatory, here are some book suggestions which you can do. The first one is the famous Gilbert-Strang's linear algebra. You can take this one as advanced. Sheldon Axler's linear algebra done right. George Shilov and Serge Lang's famous introduction to linear algebra. These two books are a little bit advanced, right? And the first and the third one is pretty easy. But I'm just giving you this suggestion because it is a must. Now also what you can do is that you can go to my playlist in vectors and tensors in physics for students, and you can see a lot of videos which are related to vectors. I mean to say you must be knowing vectors, but if you really want to brush up through those topics, go to this. I have just made 2 videos, my kind apologies, on basic vectors. But from vector, how you move into tensors, there are a lot of videos, I think around 14, 15, which you can have a look. The second one is the differential geometry, and this one, lesson number 13, is particularly important, although there are many videos, I think around 20, not 20, maybe 15 videos on differential geometry, which you can watch. But lesson number 13 is important because it helps you to learn differential geometry through learning. So what are the best books, what to read, do's and don'ts, etc. are being covered. So this is the mathematical prerequisite. So number 1 would be linear algebra, then multivariable calculus and vector calculus. That's it. And a little bit historical and intuitive understanding of what is called non-Euclidean geometry. Now we come to what are the best books for learning tensors. This is the main part of the video. I'm going to talk about that. And remember, I'm not going to talk about one book. I'm so sorry. I'm going to talk about multiple books, and then only you will be able to understand that which is the first, second, and the learning method and how to approach that. So my first book has always been the favorite Daniel Fleisch Introduction to Vectors and Tensors. Although Amazon rating is round about a 78, I won't mind that if it is 98% or so. Now this book, amazing is that the content. If you don't know vectors, it will teach you. If you don't know vector operations, it will teach you. If you don't know Laplacian, curl, etc., everything this book is going to teach you before it goes into what is called tensors. So this is absolutely an amazing book, and here you can see the tensor part, the covariant, contravariant, and then the tensor addition, subtraction. Everything is completed. Most importantly, you see this part which talks of the preparation is just awesome. So Daniel Fleisch book, it would be absolutely amazing, and you can immediately start reading and understanding this book. So if you talk about what you say, it is one self-complete book on tensors. Also, you will see that it have an easy introduction to tensors, and it offers a very clear explanation. Nothing is left unsaid, and it focuses, as I told, on the basics. It built up on the vectors, etc., and goes on. Now, here is one point I would like to mention. As a person learns more and they gets an opinion, this book has got certain, I won't say problems, but issues. issues in the sense when it moves into tensor calculus, it takes an abrupt jump in terms of mathematics. So just be aware that the book actually takes a kind of a jump in terms of tensor. Okay, so that is basically, but it is a true gem, no doubt on that. Now the next book would be G.E. Hayes' Vector and Tensor Analysis, a less known book, but it is I would say great. Now the reason is that you see the content again, it starts with linear function, scalar product, then it moves into application of geometry, then it moves into differential geometry, page number 51. As I told you that if you don't know even differential geometry, if you go through a very good book, you are going to learn differential geometry in a due course of time. You really don't have to take all the topics, etc., but you will learn in due course of time. And you see differential geometry, and importantly partial differential equations are also taken care. So it's an amazing book. So this is the chapter which you can see integration is covered, curl and vector, and then finally it moves into tensor, make tensors, and so on. So this book is actually I would say mathematically even better than Daniel Fleisch, because it gives an excellent introduction and exposition, and this Serre-Frenet formula for lines and space, these are brilliantly explained. The next book, which is Borisenko and Tarapov, Russian mathematicians, they always write great books. This is the Amazon rating. Now this book is also very good. It is very extensive. You see vectors and scalars, then it goes into basis and transformation, the tensor concept, second order tensor, higher order derivative. It's mathematical, but it is very good. And most importantly, you will see the tensor algebra is covered in details, the vector and tensor analysis. You can go through the, I would say, the part, and here it is important. Now you see this book also gives certain great diagrams, and because tensors, as I tell, is something very abstract in nature, you won't be able to understand the concept until you go through the diagrams. The other two books, GEA and Daniel Fleisch, does not provide this kind of beautiful diagrams. Cylindrical coordinates, these, that, etc., symmetric tensor, rotation. It is absolutely wonderful. Plus, it gives the mathematics part also. So if you talk of my honest opinion, then I would say it is an excellent book, and it is written in very coincised and focused style, and the sections it devotes to integral theorems look more in touch with the current trend. So that is how the book actually evolves into. So my next recommendation would be from mathematics. Let us now move into the Tensor Calculus for Physics. That would be again brilliant, and the rating is 78%. Again, this is an amazing book, and the author is this person. Now I won't pronounce, possibly it is Dwight E. Neuenschwander or something like that. I mean to say he's a German physicist. And this book, the good part is that this book talks about the physics part. Obviously there's a mathematical aspect of tensors, and there's a physical aspect of tensors. So here you see that the book says that chapter 1 is that why are not tensors defined what they are. And then you see it goes into Euclidean gradient, Euclidean vector. Amazing. What is the theory of relativity? So if you want to know more about the tensor in terms of physics, this is the book. The inertia tensor, the electric quadruple tensor. So yeah, it actually talks about the tensor part in the terms of physics. So I just given a kind of an overview. So integration, then relative motion, tensor algebra, every part of the book is covered. So more of the physics part. You see the signs of trouble. Now you see the divergence, curl, what is curvature, Riemann tensor, the covariant electrodynamics, tensors and manifolds. Everything is coming up. Everything is slowly coming up. So if you really want to understand tensors in terms of physics, then this is the book for you. This is absolutely great. And if you take my opinion, I would like to summarize it. Okay, so the tangent spaces and manifolds are there, and then it goes into exterior derivative. That means it is teaching what you call exterior algebra and all those things. Okay, So if you take my opinion, I would like to summarize that this book would be an excellent guide. Yeah, it is not lucid obviously as Daniel Fleisch's book, but it is a very good study for those who are more mathematical and want to understand the physics. So yes, university physics and mathematical tools, this would be an excellent book to go through it. Now I come to my favorite book, I would say Tensor Calculus and Differential Geometry by Prasun Kumar Naik. Now you see, if you are thinking that, oh, again I have to learn differential geometry, no. The magic of this book is that it will magically take you through the differential geometry, and by the end of this book you won't be able to understand even that you will learn differential geometry. So you see, obviously the nature of the book is mathematical, that you have to understand. So tensor algebra, it starts with addition, subtraction, contraction, etc. So it gives the operation part. Then you see the Riemannian metric. That means what? Again, differential geometry. So the line element, then the Christoffel symbols, most importantly, the covariant differentiation, curl, gradient, everything is being covered. So it is taking hand on hand with differential geometry also. So here you see the geometry, the space, the curve, even the geodesics are being covered, element of surfaces, etc. Everything. The curves on the surface, the classical mechanics, that means Newton's law. So you see the Lagrangian, most importantly, the Hamilton's canonical equations. So I see that after going through all those books, this is, I mean to say, I really don't have any word to speak about this book. Then you see relativistic mechanics. That means the book is teaching you three things. One is differential geometry, second is tensor calculus, and also physics. The relativistic part and the classical part. So I mean to say, this is absolutely a great book. I'm so sorry. So I really have no words to give you again a summary, but just pick up this book and start learning. The final book which I would recommend is this one, which is called Robert C. Redd's book on vectors and Introduction to Vector and Tensor Analysis, because that's 72% rating. And this book is also good. I mean to say, it would first start with the historical summary, which is quite a good thing, that system, etc. And the differentiation of vectors will also follow. So the content is quite, I would say, intense, and then would go into integration of vectors, fundamentals. It is very difficult to cover one by one everything, so I have skipped for that part. But it is something really important and something really great in terms of the book. So if you talk of the summary of the book, I would say yes, it is very interesting. Explanations are rigor, clear, there are no confusing errors, and the exercise most importantly are there, which will make you do, and it will clear up all those things. Now you might be feeling confused that okay, so many books, so many opinion, which one will I go for? Hold on, I will now say you that what is the chronology and how you would go ahead reading this book, which book to read first. So the first thing would be this one. I mean to say, if you want to get both the intuitive, simple, easy understanding of tensors, then I would say straight away go to Prasun Kumar Naik's book, because this is the book which will take you differential geometry, curved surfaces, tensor calculus, and the amount of physics that is required. It won't teach you everything related to physics, but that one which is required. Then you can go to Vector and Tensor Analysis, G.E. Hayes' book, because this book is also good. And if you want to learn the physics part, then you should go to Dwight E. Neuschwander's Tensor Calculus and Physics. Now that actually brings us to the end of today's video. I know that it has been very intensive and a little bit long, but yes, it was required because I wanted always to give a complete thorough understanding right from the beginning of the tensors, misconceptions, applications, rules, what you should do, what you should not do, and how you will study, what are the best books, and what is the sequence that you should go for. So I am immensely thankful for today's watching for you this video. If you like this video, click on the subscribe button and click on the bell icon to get all the notification from Physics for Students. You can always write to me at this email ID, and don't forget to subscribe to my other channel, which is General Relativity Explained, where I'm trying to put up more videos on Einstein's general theory of relativity. If you want, you can further follow me on my Facebook, LinkedIn, Instagram, and Twitter account. That's all for today's video. Please stay tuned with Physics for Students because there are some very interesting and important podcasts and videos which are coming up. Stay safe, stay happy, and please subscribe to my channel and wish you all the best.